Hey guys, this is Garrett Wong, also known as Ensign Harry Kim from Star Trek Voyager, and you're watching Astronomy Live.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Stop.
Hello folks, welcome to Astronomy Live. Tonight I'm going to be live streaming the supernova in spiral galaxy M101. So this is a recently discovered supernova, which is actually a Type 2 core collapse supernova, located in galaxy M101, discovered on May 19th, 2023. Currently visible even in amateur telescopes. Tonight I'm going to be imaging it using an 8-inch Meade LX200 Classic with an SBIG ST2000 XCM single-shot color camera and an A07 adaptive optics unit. This particular supernova was discovered by amateur astronomer Koichi Itagaki, and this is just one discovery he's made. He's also discovered a variety of minor planets, 3 asteroids by the look of it on Wikipedia. So congratulations, Koichi. So tonight we're just going to be streaming this while I acquire images. M101 is just past the meridian for me here in Florida, but I'm going to be imaging it for the next few hours, and hopefully at the end we'll have a nice, beautiful color image. Now there are a couple of artifacts in the image right now due to dust motes on the CCD. So you might be noticing a couple of donuts here. There's also a couple black spots over here and here. These are dust motes in the optical train, mostly on the CCD itself, and they will be removed ultimately by the use of dark frame calibration, or sorry, flat field calibration. So that will flatten out the light in the image and get rid of dust motes in the image like that. You can see how bright this supernova is, though. It looks like one of the foreground stars in the image, but it's actually in that galaxy. So this supernova is about 21 million light years away. And yes, that means it actually happened 21 million years ago, but the light is just now reaching us. So sit back and relax, and I hope you enjoy. Alright, apologies. I'm still getting things situated here. Had to get my blue snowball, my good microphone out here. So, this was a bit of an impromptu live stream for me. I wasn't sure if I was going to do a live stream of this, only because I'm kind of far from the house right now, and I wasn't sure if the Wi-Fi would reach, for one thing. And this was not actually the first target I went after tonight, but the first target I went after tonight required a certain degree of focus, because I was manually chasing it, which is not normal for me when it comes to satellites. But I was manually chasing a GPS satellite. And you'll find out more about why I was doing that in an upcoming video. But let's just say it's part of a much larger project that I'm working on with Red's Rhetoric, and I hope you guys will enjoy what we're working on there. But I needed to track a GPS satellite, not with direct tracking, but by tracking the stars instead and letting the GPS satellite pass through the field of view many, many times over. So I had to continually update the coordinates the telescope was pointing at, and when I would see the GPS satellite leave the field of view, I would move it ahead to the next set of coordinates, which only took about a minute, and then pull in the next set of coordinates, repeat ad nauseum until it set in the trees. So, and all while I was doing that, I was also having it imaged using a telescope in Chile. So we're going to get some parallax measurements out of that too. It's going to be visible, so this supernova is going to be visible for probably a couple months at least. Yeah, it is. I heard the weather's supposed to turn after tonight, so definitely wanted to get this while I still could, for sure. It's a pretty rare opportunity to get one of these in a galaxy that's this close, actually, and this visible. But yeah, it should be visible through most of the summer, I would think. And Lubo, your idea of doing a combined live stream, what did you have in mind exactly? I see you're doing narrowband imaging. Are you doing that tonight? I guess I should hop on over to your channel and see what you got going on there. Because as it's probably going to, the weather's going to be turning here for me in the west side of Florida for the rest of the week, so this is probably the only streaming I'm going to get to do of this supernova anytime soon. Not to mention the moon's going to get progressively brighter each night this week. Watch stream on Luca Matico. Now you guys. Current magnitude, I would say it's a lot brighter than 14.9 right there. I mean, these are 5-minute images, but it's a good question. I'd have to run some comparisons to other stars in the frame. Let me see, where's my phone? Let's just put this in context with some other stars in the area. Okay. Yeah, if I'm reading my sky chart correctly, that's 13.4, that's 11.5. Okay, so let's put this in context. If I'm reading things correctly, this star, I have it in a Gaia database at magnitude 13.4. Whereas this one up here, you can tell it's brighter, I would say this star up here is a little bit dimmer still than the supernova, just by eyeballing it. And this is 11.48. This is TYC TICO catalog TYC 3852-1108-1. And that's 11.48 right there. So, I'd say the supernova right now is actually brighter than that. So, brighter than 11.48. So, yeah, I mean, if I stuck an eyepiece in there right now, I would expect that it's bright enough I'd see it visibly in the eyepiece with an 8-inch scope. So that's pretty dang cool. Chuck's Astrophotography says, I'm still capturing the supernova and it seems a little brighter than when I captured it 9 days ago. I can totally believe that. Sent me an image via email. Oh, you talking to Lubo there, Shamrock, or are you talking to me? I guess I should check my email. Oh, yeah, okay. Yeah, I got the image. That is 12 3-minute subs. Oh, that's looking good. Yeah, that's looking good, Shamrock. So you're on it tonight then? Okay, I didn't know if you wanted me to tell people who that was. Yeah, hey Bob the Science Guy has joined us from Shamrock Banks Observatory, so thank you. Appreciate you being here. I'm a little annoyed with my camera. I have to run it warm tonight, above 0 degrees Celsius. It's frosting up the CCD again. I had just replaced the desiccant this weekend to do the imaging, some imaging I did of via Sat3, and I was able to get it down to cold temps, and that was fine. But here we are Monday night, and from Saturday to Monday, it's now. Humidity's climbing in the CCD chamber, so I can't get it down to cold temp. Not so happy about that. But I probably just need to replace the desiccant. It's old. I microwaved it to heat it up and try to bake it out, but apparently it was only partially effective. But I've had it a couple years now. I mean, I usually replace that stuff. I don't know if anyone has any tips on doing a really thorough bake out on silica desiccant without destroying it. Let me know. But for a few bucks, I suppose it's worth just ordering some more stuff. Actually, now that I'm thinking about it, I should go ahead and place that order so I don't forget later, because I will. Yeah, for $6 it's worth just getting some fresh stuff. So I'm gonna go ahead and pop that order in over to Jeff Bezos and get myself some more desiccant. Oh, what mount do I have? This is an 8-inch LX200 Classic on the original fork mount. And I'm using an SBIG ST2000 XCM and an A07. So you've got you also have the same scope. You've got the 8-inch LX200 Classic on a homemade wooden wedge. Wow, that's brave. It gets the job done. I mean, if it works, I'm not going to knock it if it works. I do find, I mean, I don't know how it is with you, but I find the LX200 mount is, well, it's not brilliant, is it, for long exposure astrophotography like this. But with the A07, it really seems to cure things. Like, I don't have any complaints about how these 5-minute subs are coming out at all. You are sort of, you know, hamstrung by the A07 when you do that. You have to have a good guide star. You know, something that you can do sub-second exposures on. Like I'm doing half-second exposures on my guide star here. So I'm guiding at about 2 hertz. And that really, you know, takes out the wobbles with the gears on the old LX200. And yeah, I've trained the periodic error, but it's not perfect. Lubo says, by the way, tried ASI Air Mini, and I'm very pleased with the results. That's cool. Yeah, I've heard about those newfangled ASI cameras. So they do, whether they do wireless transmission to the computer? I'm not super familiar with modern equipment, I guess you could say. I mean, I'm still rocking early 2000s equipment here. ASI Air. So, oh wait, that's the add-on, right? You can plug into various different ZWO cameras. Is that the deal? That sounds cool. I mean, that sounds fun. More fun than running a whole bunch of cables back, right? But I'm just here with the retro setup, the old LX200, the old SBIG ST2000. It's all platform. Oh, it's the whole platform. No need for the computer. Well, there you go. I mean, that's nice. That is nice. Is that the one that's basically like a modified Raspberry Pi? So it does it all on this mini computer, basically? Or am I thinking of a different product? Like I said, I'm not super familiar. Mark says he was using Raspberry Pi with Astroberry, similar to ISI Air. Now I use a cheap laptop to run everything. Yeah. Ah, can I explain the numbering naming system for newly discovered stars, etc.? Also, who has to confirm that a new discovery is actually new? Best wishes from UK. It's a great question. So, the Supernova naming convention, I mean, I'm not as familiar with that as I am with the comets and asteroid naming conventions, but I assume it is just as systematic. I mean, SN 2023, pretty self-explanatory right there. It was discovered in 2023, right? IXF, though, I'm not sure how they index that compared to asteroids, to be honest. I know the whole numbering system for asteroids, it's the half month that the asteroid was discovered in and the order it was discovered in. I imagine with Supernova, it's pretty much an index just based on discovery order. In terms of the discovery, yeah, mosquitoes are starting to come at me. I've got a citronella candle burning, but it's starting to become ineffective. So, clearinghouse for that. I think it's the IA. Is it the IAU for that? Okay, yeah. Transient name server is official mechanism for the
IAU mechanism for reporting new astronomical transients, so IAU does report on that for Supernova. Services provided by the IAU Supernova Working Group. Let's see. And the naming convention, let me see what I can find on that. So yeah, IAU reported to the Central Bureau for Astronomical Telegrams, the IAU Bureau, and automatically given provisional designation based on the coordinates of the discovery. Ah, okay. Historically, they were identified belonging to type, blah, blah, blah. Supernova's permanent designation is formed by the standard prefix SN in the year of discovery, so SN 2023, and a suffix composed of 1 or 2 letters of the Latin alphabet. First 26 supernova of the year receive a capital letter from A to Z. Subsequent supernovae of that year are designated with pairs of lowercase letters from AA to AZ, then continue with BA to ZZ. For example, prominent supernova Super SN 1987A was the first one to be observed in 1987. And since 1885, the letter suffixes are explicitly assigned regardless of whether only one supernova is detected during the entire year. So I hope that answers the question. So it kind of, as I suspected, it's systematic and it's based on the order for the permanent designation. This provisional designation is based on the coordinates, but that's not what we're dealing with here. We've got the permanent designation, SN 2023 IXF. Corey says he's got an early 2K 6-inch reflected manual equatorial mount. Motor broke, I think, and 10-inch Dob all manual. Nice. Well, sorry your motor broke. That's unfortunate. I used to have a I guess it was late 90s 6-inch Newtonian. Well, not Newtonian. It was a yeah, no, it was a Newtonian reflector on a equatorial mount with a clock drive, mechanical clock drive, battery powered. I think it took 9-volt batteries, but it was all manually driven in terms of pointing it at things. ASI Air is its own computer. It doesn't need to be connected to anything once you tell it what to do. That's cool. So, I'm curious about that. I need to be educated on the aspects of modern equipment and what it can do. With the ASI Air, like, you say it doesn't need to be connected to anything. So, how do you tell it what to do? Like, if I tell it, okay, I want to tell it to stop imaging so I can go refocus the telescope. Now, you know, that's the unfortunate thing with using a Schmidt-Cassegrain like this with mirror flop issues. Like, as it rotates through the sky, you need to occasionally do a refocus on it. I mean, I guess that's true of a lot of scopes with changing temperature over the course of the night anyway. But I'm curious how you control it for things like that, and how do you control and monitor auto guiding? Like, does it connect to your phone? Can you wirelessly connect it to your phone to monitor how it's doing or whatnot? I guess it's, yeah, I'm just curious at how that actually works in practice. And Caleb Ray asks, it's in the Pinwheel Galaxy, right? Yes, this is in M101, which is also known as the Pinwheel Galaxy. Monitor through phone or iPad. Yeah, okay, that's cool. I do like the sound of that. Make a plan, it will follow the plan. Okay, yeah, that makes sense. All the sequences are pre-programmable. Yes, you can use phone or tablet. I like the sound of that. I do like the sound of that. Just laying back on your tablet, monitoring it. Or computer using Android emulation. Yeah, that sounds... I mean, it's nice that you can do that, but that sounds a little tedious, I guess. Just a lot of bits to have to go through on that one. Thank you, Yvette. Hope you enjoy the view. Wouldn't be easy to feed that into YouTube or other streaming software. Yeah, that's a question, SMA. Yeah. I wonder how that works in practice. I mean, I know YouTube's got streaming software, but in practice, how do you... I mean, I guess you could capture what you're seeing on your tablet and then feed it through YouTube's tool. Or you could do the Android emulation route to stream it from your computer. I've noticed that TikTok streaming has become quite popular for amateur astronomy. I've noticed a lot of people on TikTok streaming the moon or the sun, what have you, even deep space targets at times, on their phones. And I've been wondering about that. Like, how are they getting their images from their telescope on their phone, especially for deep space stuff? And I say on their phone because, I mean, it's in, portrait vertical format. Looks like it's being pulled off a phone. I suppose they could be using ASI Air. So in some ways, it might make things easier for doing things like that, I suppose. What's the approximate size of the sky we're looking at? It's a great question. So, you're not even seeing the full image size here. It goes out this way, a good bit. I'm trying to monitor the auto guiding while the picture's taking, so I've got the auto guide window up there in the top left. But the total picture has a field of view of about half a degree, or about 30 arc minutes in width, and I want to say about 24 arc minutes in height. Again, that's the full height of the image, so it goes from up there all the way down here to the bottom. So I am getting pretty much all of M101 there, but we're just looking at a zoomed in view here to really see that supernova well. Organized back there. So you could just barely fit the moon width-wise in the image, but the moon wouldn't quite fit in the vertical axis on the image. Yeah, Kitsune Cavalier says, I'm glad TikTok streaming isn't just for flat earthers. I am too, though. I did see someone live streaming, ranting about flat earth, ranting in favor of flat earth on TikTok today. I didn't watch or listen very long, but it sounded like they were having a bit of a argument with their chat. I mean, just kind of straight up insulting their chat, to be honest. Which, I mean, that doesn't seem enjoyable to me. That doesn't sound like much fun, to be honest. But I suppose if you sincerely believe that stuff, then I guess you would want to proselytize about it. But it's so sad to see that kind of thing. Especially when someone seems like they're really emotionally invested in it. Like, they truly think that people like me are lying to them. Live stream from computer using OBS for virtual camera. Yeah. No, I don't think TikTok is, I mean, I don't know the platform as well as I do YouTube, but I don't feel like they're really shadow banning people for, how does YouTube put it, not edge beliefs, but sort of, edge cases, I guess you'd say. I forget the exact terminology they use. But fringe content, as it were. So I suppose that would make it a popular target for Flat Earth to flock to, since they can get their message out there unimpeded by the algorithm, I suppose. Fringe, yeah. Yeah, I think it definitely qualifies as fringe. I do feel like they're going to be, the Flat Earthers are going to be quite displeased with the video that I've been helping Red's Rhetoric with lately. It's massive. It's going to be massive. Just in terms of the amount of work that went into it, it's, I'd say, easily the most complicated, the largest effort we've ever made on any video. Any single video. And tonight it involved me tracking and measuring a GPS satellite from here in Florida and from down in Chile. Simultaneous observations with a telescope down there on the iTelescope network and my own scope here before I started shooting M101. So I'll give you guys a little taste of what I got. So again, I mentioned this before. I did not do direct tracking. I didn't use Sat Tracker tonight on that, actually. I didn't want to direct track it. I wanted it to streak through the view. It just makes it easier to measure the coordinates by astrometry when the stars are all nice, tight little round stars, so you can precisely measure the coordinates of the image. And then you can measure the start and end of the streak to get the coordinates of the satellite as it streaks through the view. For viewing purposes, and for live streaming and things, direct tracking makes sense. It's the easiest way to just keep the satellite in the frame and view it. But for measuring the coordinates very, very precisely, you want to do astrometry, which is where you measure the coordinates of the image using the stars in the image. So the best way to do that is to let the satellite pass through the view. So I brought up the coordinates of where the satellite would be at every minute through the night and manually fed that into the telescope's hand controller once a minute, because that's about how long it took to streak through the view. Maybe a little bit faster than that, actually, but between the time it took me to punch in the coordinates and slew the telescope, the whole cycle took about 1 minute. So I was taking pictures here in Florida and again, taking pictures in Chile as well with a telescope on iTelescope.net. So I can load up that video. So this was Navstar 78, which is one of the United States GPS satellites. let's see. And I was running the camera in 2x2 binning, so it doesn't have color data, but it trades off sensitivity for color. So let me show you guys that. Oh. Don't know why it's cropped in like that. There we go. So there's the time lapse of a GPS satellite flying by. You can see the satellite doesn't take very long to pass through the field of view, but of course this again is a time lapse. It actually took about a minute to fly through, and then I jumped ahead to the next position and let it fly through again. And so I'll be able to measure the coordinates tomorrow using these images by doing astrometry on the stars. So that's what a GPS satellite looks like in the telescope. And those satellites are not at geostationary distance. They're actually a bit closer than geostationary satellites. In fact, they have an orbital period of about 12 hours instead of 24 hours. So they orbit Earth twice a day instead of geostationary or geosynchronous satellites that orbit Earth once a day. Which is why if they're on the equator, geosynchronous satellites are actually geostationary. They orbit at the same speed that the Earth is turning. But GPS satellites are traveling a little bit faster, and so they orbit the Earth once in 12 hours. I really don't spend much time arguing with flat earthers, Dimitri. Honestly, I don't. For me, doing videos like I just showed you, like tracking the GPS satellite, that's the fun of it, the challenge of it. To make very precise measurements. I mean, the whole flat earth thing, to me, is just an excuse to stretch myself and sharpen my skills. But in terms of debating them and arguing with them, nah, not really interested that much. That's why I'm here tonight streaming a Supernova instead of, you know, having an argument with them, streaming a debate or something. I mean, props to people who do like MC Toon on a regular basis. I think there's importance in educating people and setting the record straight. But that's not the interesting part to me. The interesting part is doing the astronomy. Did a couple of those scenes capture Moon Venus? Sorry, you mean the pictures I was taking tonight? I did not capture the Moon or Venus tonight. I did peek at the Moon through the telescope while I was aligning it, but no, I didn't take any pictures of it. The setup that I use for taking pictures of the Moon or Venus is quite different. I usually have the Blackmagic camera attached to the telescope for that. This camera here is optimized for deep space work. This kind of imaging, where you're doing long exposures, 5 minutes long. It does not have as much resolution as the Blackmagic, and it's certainly not capable of the kind of frame rates that the Blackmagic is capable of. This is a relatively slow camera. You can see in the bottom right how long it takes to download an image. Here in 12 seconds it'll finish another image. Watch how long it takes to download that image from the camera. This camera is an old USB 2 camera, and its download speed is not great, but that's fine for deep space work because we're not interested in high frame rates. See, even as I'm talking, it's still downloading that picture, downloading that picture, downloading that picture. Now it can start taking a new color picture. That's how long each frame takes to record, and that's just not what you want when you're doing lunar or planetary imaging. You want high speed, high frame rates to be able to capture the moon or the planets many, many times a second, so that you can then stack or average those frames together to get the best quality picture. So I like to use the Blackmagic camera. That is definitely unconventional, I'd say, for lunar and planetary imaging. But the reason I use the Blackmagic is because, as you probably know, I also like to film a lot of rocket launches. And so it's nice because it's a self-contained unit. It, can record video all on its own. It doesn't have to be hooked up to a computer. And so for that reason, I like using it. It's got excellent dynamic range, excellent frame rate, 4K, 60 FPS. So it's excellent for doing satellite tracking as well, especially for the space station, imaging the space station. And again, because it's a self-contained unit, it doesn't have to use up any of the CPU horsepower of the computer. So the computer can be focused on doing things like calculating where the rocket's going to be or where the satellite is going to be, and I don't have to burden the computer at all with the camera. So that's the trade-off that I made there. If I were just doing lunar or planetary imaging, I would go with a much more conventional astronomical camera that's optimized for planetary imaging, which again is going to be something that has very high frame rate, probably full frame shutter. I just don't like having to deal with rolling shutter artifacts. That's just a pet peeve, and that's something I have to deal with the Blackmagic, but that's an acceptable trade-off to me because, again, the kind of photography and videography that I'm doing requires it. Also, I mean, onboard sound capture. It's something so simple, but it's something that an astronomical camera would not come with. An astronomical camera is not going to have. It's not going to be set up for capturing sound, but the Blackmagic has a microphone input, so I can put my dead cat on there and get the sound of the rocket launch, which is very important. Does the supernova really look like that now, expanded enough to the point that it doesn't look like a star anymore? This is what the supernova looks like, at least to my telescope right now, and it is very star-like. Now, if you had Hubble or the James Webb, when will they be able to resolve something? That's a question, and I'm sure within a relatively short period of time they'll start to be able to see something. I bet. So we'll see. It might take, who knows? Might take a few months. I'm not sure, but I'm sure at some point, really high-end professional telescopes like Hubble and James Webb and others will start to see more detail. What does guide rate mean? Well, that's very important, isn't it? Very critical for this mount. So guide rate is 1.9 hertz. That means 1.9 times a second. The adaptive optics unit is turning the mirror, the small tilt tip mirror that's in the adaptive optics unit, to keep the star in the top left centered. So that's a star that's actually not in the field of view. It's just up and out of the field of view, and it's being captured by a small secondary camera that's within my camera. So the deep space camera I have actually has two CCDs, a guide CCD and an imaging CCD. They work independently of each other. And so the guiding chip is imaging 2 times a second right now of a star, a small star that's up and out of the field of view, and it's using those images to drive input to an adaptive optics unit that is attached to the camera. And that adaptive optics unit has a tilt tip mirror system that actuates using basically electromagnetism, kind of in a manner similar to the way a speaker creates sound. And so it's able to respond very, very quickly and issue a corrective command to keep that star centered. So you see in that window, it also has X error and Y error in fractions of a pixel. And so it's monitoring that 2 times a second and updating the tilt and tip of the mirror to keep that star centered. At a high enough guide rate, that actually starts to correct some of the shift in the image due to the atmosphere, but it also corrects shifts due to imperfections in the drive system. So the LX200 drive system is not perfect. The gears are not perfectly round. And so even though I'm polar aligned, and I think my polar alignment tonight's pretty good, it's not going to turn at exactly the rate it needs to. It should turn at about 15 degrees an hour, but because the gear is not perfectly round, during some portions of the gear's period, which is about 8 minutes. It takes about 8 minutes for the gear that is driving the right ascension axis to make one complete revolution. At certain points during that revolution, it's moving a little too fast, and at other points it's moving a little too slow. So even though on average it might be moving the right speed, at specific moments in time it's either moving a little too fast or a little too slow, and that'll cause the stars to wobble. So using the adaptive optics system takes that out. You can use auto-guiding as well. Traditional auto-guiding just tells the telescope's motors, you're starting to drift a little bit, turn. The problem with that is, especially with a lower end mount like this, there's slop in the gears. When the gears have to reverse direction, it takes seconds, a few seconds, for them to take up the slack and start to turn the other direction. That's no good. By the time they've corrected for that, by the time they've taken up the slack, the star has already started to blur the image. The image is already becoming blurred by the imperfections in the drive system. So using an adaptive optics system with a tilt-tip mirror, it can respond instantly. No hesitation, no delay, no latency. It's immediate, essentially. And so it's able to guide at multiple times a second instead of once every few seconds. And that makes all the difference in the world. That's why the stars in the image look, frankly, so good on an LX200. They have no business looking this good on an LX200, frankly, with a 5-minute long exposure. Because, again, as I said, the period for the gear is 8 minutes. So in 5 minutes, you've already completed almost one full revolution of that gear, and it has been wobbling back and forth during that time. But you don't see it here because the adaptive optics system is correcting for it. As it reaches towards the edge of where that mirror can tilt, you see X tilt and Y tilt in percentages there. Right now, X tilt's at about 50.8%. Y tilt is at about 67-68%. As it gets too close to the limits of travel of that mirror, it will move the motors to force it back within the range that the tilt-tip mirror system can handle. But it can do that much slower without noticing any effect on the image, because the tilt-tip mirror system is doing the bulk of the work, even as the motors are catching up. So it'll keep it within about that range. It'll keep it probably within 70-75%. And then the motors will kick in and slowly start to take up some of that slack. So it's not about, thick grease or graphite for wobble absorption. It's not about like a wobble, like some sort of vibration in the motor. It's like the motor itself, the gear that motor is turning, which is a big gear, frankly, is not perfectly manufactured. It's mass manufactured, and it's not perfectly round. And so as you turn that with an electric motor, and you might be inputting a fixed voltage, and you might think you're supposed to be getting a fixed speed out of it, you're not getting a perfectly fixed speed. And you got to think about this: the moon wouldn't even quite fit in the image you're seeing here. So a tiny fraction of a degree is all it takes. Each pixel here corresponds to about an arc second, 1/3600th of a degree. That's all it takes for it to start to blur the image. And so anything less than perfection in that gear is going to result in a wobble, and no amount of grease is going to fix that. That's just inherent in the shape of the gear. So the solution is not with, at least if you have to use that gear, and I do, because that's the budget I've got, this is the scope I've got for deep space work, the solution is not to, grease up the gear. The solution is really to use adaptive optics or auto-guiding to fix that. Alright, sorry. Yvette had a question here. Can anyone assess the telescope in Chile? Are you talking about the telescope that I used in Chile? It was a really nice scope, but that's on the iTelescope network. That was T70 on iTelescope. Not sure if that's what the question was asking about. I did mention that I had used a scope in Chile tonight. And I'll put a link in the chat on that scope. I don't have those images processed yet. So this one is really optical too. I shouldn't even really be calling it a scope. It's a Samyang lens, but the camera is an astronomical camera. It's basically a 135 millimeter lens with an astronomical camera for very wide field views, which is what I wanted for getting that GPS satellite passing through the field of view. But I think there was another question there that you had. Let me see if I can find it. Scrolling back up through the chat. How much does a good camera telescope cost to view the stars and planets? That's a great question. If you just want to see the stars and planets, and you're not trying to do, astrophotography like this, which I would recommend starting off just with visual observing, binoculars, learning to navigate the sky using star maps, and learning to star hop. A good scope to start on would be a Dobsonian telescope, I think. So a Dobsonian scope is very simple to operate. It's basically on a big turntable with the other axis just able to point up and down, rotate the scope in this turntable, essentially. And so it's what we call an altitude azimuth scope, so it points up, down, left, and right. And you've got your Telrad or viewfinder on there to be able to locate what you're looking for, at least the initial star you're looking for. Then you look through the eyepiece and star hop to your destination. So star hopping is where you look in the eyepiece at something that you found in the viewfinder, usually a relatively bright star that's somewhat close to your target. But then you have to do pattern recognition, essentially. You learn to do pattern recognition of what you're seeing in the eyepiece. And with other star charts, you know to go from one star to another star to another star in the view until you get from point A to point B to point C to point D to you get to your target. But it's a very useful skill. It takes a little bit of practice. But this is how you locate deep space objects like M101 in a manually driven scope. There's no motors on it. It doesn't find anything for you, and it doesn't track the target for you. But you get the most bang for your buck. You can get a very large Dobsonian telescope for a lot less money than a smaller motor-driven scope like this. So a good 8-inch Dobsonian would be a good way to start, even a 6-inch. But again, some of these skills are best learned, I think, with binoculars, because that's just the easiest thing to operate is binoculars, a good pair of binoculars. So you get a good pair of 18 by 50 binoculars, something like that, or maybe even less magnification than that. I've got a pair of 10 by 80s that are really good, and or is it 10 by 60s? No, I think 10 by 80s. That would be really big. I think they're 60 millimeter optics. So yeah, they're like 10 by 60s. Really good pair of binoculars for general use as well as for astronomy. Let me see if I can do some initial stacking. Of the images I've got so far. question is, do I have some calibration frames from earlier runs that I can throw at it? That's the question. Yeah, I don't know how well old flat fields are really going to work, but I'll try it. Let's see. It's worth a shot anyway. Hey, we got a satellite streaking through there. Ooh, see that streak cutting across the left side of the image? Let's see if I can identify what that was. Awfully late for a satellite. Closest satellite would be Integral, launched in 2002. Doesn't look like it should have been in the field of view. Oh, wait, there was something else. What do we got here? What do we got here? Oh. There was a Starlink. Where did you go? Starlink 5692. Oh, wow. Yeah, okay. What? At 12:50 in a couple minutes, I'm actually expecting another Starlink 1916 to come through the field of view, according to Sky Safari. Now, the question is, when were the elements updated? Wednesday, May 24th? Okay, that's slightly out of date. Yeah, those are some old elements. Let me see if I update the data, what it says. But yeah, we're possibly going to get run over by Starlink satellites while imaging here. Okay, finally. There we go. So, let's see. Okay, I'm not seeing that Starlink satellite now. After updating the elements, it's saying, oh, no, that's not there. Pay no mind. 1020 flew by very close. Might have been in. Yeah, that might have been Starlink 1020. Okay, no streak there on that one. The way it was flashing, though, suggested it was, like, rotating, tumbling. Starlink 1020 got a problem? Don't know. Maybe. It was very, very close. Might have been in the field of view. But okay, that was interesting. So we've got Starlinks out there tonight. The closer we get to summer and the summer solstice, the later into the night Starlinks will be visible for us here in the northern hemisphere. So they're more of a factor this time of year than in the winter. This telescope's in Florida. What would a big geostationary satellite in the 60s sci-fi look like? I don't know. In 60s sci-fi, probably cardboard and tinfoil. But then again, real geostationary satellites often have mylar foil, so kind of the same thing, huh? My view will be, I think it will be mirrored. It literally has a AO7 mirror on it, so I think it's going to be vertically flipped. Yeah, I'm 90% sure this is a vertically flipped view from the mirror. Okay, let me see. I'll add in that additional image from just now. So this will be an hour and a half of light that I'm stacking right now. No idea if the flat fields that I'm using from a much older run on a previous night, actually from 2022, are going to work or not. My guess is probably not. This will probably fail in terms of calibrating the dust modes, but we'll see. Yeah, that's a hard fail on those dust modes. Let me see if I can get a better flat field subtraction out of something. Surely something somewhere I've got. Now I know these flat fields were good for that night. My old Orion Nebula picture. These flat fields are garbage. But whether this will actually work for tonight's images for flat fields, no earthly idea. Oh. Okay. This might mess things up. Okay, apologies if the stream goes wonky here for a bit. Okay, flat fields, yes. Alright. Try this again. Okay, that's much better. Excellent. Let's see. I'm going to adjust the brightness and contrast on the image, and then I'll share it. This is looking pretty cool. Yeah, this is going to be a nice image. So this is just a quick and dirty processing, not really doing proper tone mapping. But this is the first 90 minutes of images. I'm gonna bring it up here. Oh yeah. That is looking pretty sexy. Supernova is right there. Oh, looks like I missed Bob exiting. Have a good night, Bob. Oh yeah, so I see what you're saying about the binocs. The thing about the binoculars is you're going to be viewing from an altitude azimuth perspective, so field rotation is going to be a factor, and that could completely change which quadrant it's in. I can't really tell you what quadrant it's going to be in because it's going to be depending on your location and the time of night at your location. And so the easiest way to find it in terms of locating what you're looking for is it's next to, what is this, NGC 5461. That's that bright bit of nebulosity that is next to the supernova. This down here, this guy right here, that is NGC 5461, and then the supernova is right next to that. So you've got NGC 5462 down here in the arm, NGC 5461 up here in the arm, right next to the supernova, and then there's the supernova. So even if the supernova is not listed on your preferred planetarium software, whether you're using maybe Stellarium or Sky Safari or the SkyX, whatever you have, if you look at it and you look up NGC 5461, you can see where it's going to be in relation to the core of the galaxy from an altitude azimuth perspective at your location and your time. So that's how you can quickly and easily locate the supernova, even if it's not listed in your planetarium software. So the darker image, yeah, this darker image here, this is after processing, stacking an hour and a half of light, doing the brightness and contrast, and this is the full frame of the sensor. The image, the live image we were looking at back here, this is just a portion of the total frame. It's zoomed in a little bit, so this guy here is probably closer to the true resolution, though even this is actually not quite the full resolution of the image. The full resolution of the image is 1600 by 1200, so the vertical resolution is a little higher than what I can put out at 1080p. But it's close. It's very close. And I'm quite happy with how that's coming along there. Again, without any kind of fancy processing, with just an hour and a half of light. I'm pretty happy with that. From the look of the moon right now, I'd say we're also getting a little bit of haze coming in here. Might be getting fog coming in later, I don't know. Let's see, what's the current elevation of M101 for me? 54 degrees, so that's not bad. But it's probably a little less well-defined than it was at the start of the stream, just due to the slightly lower elevation and due to the higher degree of haze in the atmosphere now. Though I'd say the image from 5 minutes ago, before that car drove by, I turned on my neighbor's light. Thanks. But the image from before was actually pretty similar to the image that I had at the start of the webcast. In terms of quality, I'm just looking at it in Deep Sky Stacker. Yeah, quality-wise, I'd say it's pretty similar. I am wondering if a focus run would be called for. I think it would be called for at this point. A little bit of a focus run might be warranted. Okay, what do we got on this image right now? How much time? Another 3 minutes roughly. I don't know. Actually, I'm looking at it now. It's probably well enough. What's the worst that could happen, right? I'm trying to look at it in Deep Sky Stacker and saying, maybe the stars are a little more bloated than they were. Just a tiny bit. Which would be down to the focus. As the mirror shifts under the weight of gravity. It's pretty high declination though. It's like 54 degrees, something like that. So, polar aligned, the mirror is actually not moving all that much at that declination. So hopefully that means the focus isn't shifting too bad. But I still think it's worth a look. Yeah, I think it's worth a look. We will examine the focus in a minute and a half. So I'm going to stop the run in a minute and a half. We'll zoom over to a nearby bright star in the constellation Ursa Major. And we'll double check the focus and tweak it if needs be. And then we'll resume imaging on M101. Can I stop a timed exposure if I fear that something like clouds might affect the image? I can stop it prematurely, but then it's not comparable to the others. So it does no good in the stack. In fact, it throws things off a bit. So there's no real salvaging an image if something happens. If something happens during that 5 minute period, well, you've lost 5 minutes of your life. That's how that goes. Not much can be done about it, to be honest. So, 30 seconds. After 30 seconds, we'll download the image, we'll stop the exposures, and then we'll slew over to a star and double check focus. Okay. Yeah, I'd say the haze is getting worse. Notice how much the image gets brighter, and the galaxy's kind of getting hidden by that. And that's just down to haze, unfortunately. Maybe it'll get better, maybe it'll get worse. We'll see. In the meantime, though, for those who missed it, I'll bring back up the stacked picture. So this was, again, the first 90 minutes of light stacked. And that's the result. I'm already pretty happy with that as a result. I mean, that's just pretty. We'll go to Alkaid as the focus star. I got the focus mask on. This is a Batinov mask. It's going to create diffraction spikes in a bright star. Okay. So it should be perfectly symmetrical. I'd say it could just use the tiniest of tweaks. I don't think it was that far off. I don't think it was enough to really affect the image quality. In fact, gosh, that's almost well enough right there. My computer's running low in storage space, and that's fun. Okay, let's see. There's 5 gigs back. Okay. Let's free up some more space, if I can. Okay. Alright, now that I'm done trying to free up space, let me grab a subframe of this. Grabbing a subframe lets me grab just a piece of the image for faster download speeds. Okay, now I'm going to tweak the focus. Just gave it the tiniest little motion. Okay, that made it worse. Okay, back the other way. Let's see what we get. That's better. Okay, just the tiniest little bit more. Okay, could probably use a little more. Wait, am I going the wrong way again? I don't know. Give it a little more. I'm either going to make it better or I'm going to make it worse. Okay, I think I'm making it worse. Yeah, I'm making it worse. Okay. Yeah, I forgot. You guys can't even see what I'm doing. You're seeing that. Okay, let me turn this off for a second. That's what I'm doing. There's my diffraction spikes on Alcade. Trying to get this perfectly symmetrical, and I think it's pretty good right there. Yeah, I think our focus is pretty good. Okay. Okay, now I'm going to have to reframe the shot. Okay, so it's hard to see, but the galaxy is kind of above center, slightly to the right. Now it's centered, but slightly to the right. It's a fuzzy little thing near the middle. Okay. Okay, that looks pretty good for positioning. Let's see if the autoguider's still got the star that I was using. No, it does not. Okay. Well, that's not great news. That's what we call bad news. Okay, there we go. We got it back. Yeah, I want my bright guide star again. There we go. Auto guide on that. Okay, auto guider's running. Star brightness isn't great. I'm gonna increase the guiding exposure a little bit to compensate. I go to 1x1 binning. Okay. Set up the camera again. So we're going to do 5 minutes, 1x1, auto dark. And take images. Okay, so now we'll take a fresh image. It'll have to take a fresh dark frame after that. And then we'll be back on course. What does M87 look like? Well, I can see the jet coming from the black hole in M87 with this telescope setup. I've shown it before. In fact, I did a stream on it a couple years ago. So the diffraction spikes, the purpose they serve is to allow me to check the focus. The center spike that you saw a moment ago should be running directly through the middle of the other spikes that form the X. And if you're in focus, the center spike will go right through the middle of that X. Otherwise, it will be either above or below the center of that X in the orientation I had it there. So you want to bring that center spike through the middle of the X. If it is, then you're in focus. It was pretty good before I even adjusted it. It was very, very slightly off. I mean, minuscule. But that Batinov mask is very sensitive. So even the slightest bit of loss of focus will be detected, really before you would even practically see it. Yeah, it's a really cool tool. I do love the Batinov mask. It's really essential, I think. Yeah, Betelgeuse should look nice whenever it goes off. Just hope I'm not imaging Betelgeuse with this telescope and this camera when that happens, or it'll probably fry the camera. This camera is exceedingly sensitive. Yeah, so sorry if I didn't explain that well before, but what I had up there for a long bit there, this was the stacked images. This is the 90-minute stack. You can see the supernova there. So this is the first 90 minutes of light during this stream, stacked, and then contrast adjusted, background light subtracted. Interesting that I'm seeing that rainbow effect again up in the top right corner. I've seen this before with the adaptive optics unit sometimes. I saw this with, I think, M57. Like this rainbow color pattern appeared in part of the image. And I think it's somehow being caused by the adaptive optics mirror. Maybe it's under a certain amount of strain or something when it's working, I guess. I don't know. Something causes a rainbow reflection to show up in the images sometimes, and I think the only time I've seen it is when I'm using the A07, which makes me think that's what's causing it, is the A07, the adaptive optics unit. But considering this scope's motors and mount are not good enough to do this under normal circumstances, I'll take that trade-off. I'll take that trade-off all day long. Yeah, it's funny, even in these 5-second exposures that I was just setting up to align where the galaxy was and everything, even though the galaxy core is just faintly visible here, you can already see the supernova. It's right there. It's bright compared to the galaxy, which you can barely see. It's just like a little fuzzy noise pattern in the middle. But the supernova is outshining the core of its own galaxy, and that's common for these core collapse supernova. They're brighter than their own galaxy. Okay, so now here comes the full resolution picture. This has hot pixels in it. That's what all these colorful pixels are. These are hot pixels, and those are just effective pixels. Every camera has them, but you really see them in these long exposures with the exposure cranked up like this. So to correct for that, it's going to take a dark frame now. It's closed to the shutter of the camera. The camera's got a mechanical, physical shutter actually. So that shutter is now closed while it's taking another 5-minute picture. And that will be used to calibrate the image. So it will subtract what it's taking right now from this image and from all images going forward, and that will get rid of the hot pixels. And they're very colorful because each pixel is pre-filtered for a specific color. This is a single-shot color camera. In fact, it's the same CCD that's actually on the Mars Perseverance and Curiosity rovers as a single-shot color camera. The KAI 2020CM is the chip designation. And so this chip has an array of 1600 by 1200 pixels. Can't find my cup holder. But those pixels are pre-filtered for red, green, or blue. And it's actually a repeating matrix of 2 green, 1 red, 1 blue pixel all over the whole image array. And so if only 1 pixel in that 4-pixel square is defective, which is statistically most likely, that's the only one lighting up. And so it ends up responding as if it were a really red or a really green or just a pure blue pixel. Because again, it's a single shot color camera, and just like a consumer camera that's single shot color, the way this works is a repeating pattern, a matrix of pixels that are filtered for these colors, red, green, and blue, and it reconstructs the full resolution image out of that through interpolation. But with only a single pixel in that 4-pixel array, that repeating pattern of 4 pixels being defective, it responds as if it's a bright red, green, or blue little star or light. But it's really just a single pixel defect. So I hope that makes sense. Makes sense in my head anyway. Why 2 green pixels? Because, well, there's a couple reasons. One, you want to make a matrix of 4 so that it repeats evenly over the whole image. So it's easy it's easiest if you double one of the 3 colors that you're doing. But also, our eyes are most sensitive to the green portion of the spectrum, and so it helps actually make an image that is more analogous to what our eyes would see. Now, I say that. I guess that's true enough, but our eyes are really insensitive at certain wavelengths when dealing with really dim stuff like this. And in fact, the cones that allow us to perceive color, our color vision comes from our cone cells, and those don't respond at low light levels like this. Like if I were looking in the telescope, my cones wouldn't fire up at all, and I would have to wait and dark adapt, and the rods in my eyes, the rod cells in my eyes, would be the only things responding to the light, the very, very dim light of this galaxy and the supernova. So if you look through a telescope, through the eyepiece, you won't see color. It'll look almost like black and white. It'll look kind of grayish. And even if you're looking at a bright red nebula like the Orion Nebula, your cones are very insensitive to that light, and you won't see red. You'll just see this murky grayish. I kind of see it sometimes with a little bit of a greenish tint, but grayish light, because your cone cells aren't designed or capable of operating at these very low light levels. The camera obviously is. It doesn't have cones and rods. It just has pixels, red, green, and blue pixels. And they're either able to detect the light or they're not, but they operate like that. So they can perceive the color that our eyes can't perceive, because our eyes process light instantaneously. Obviously, they don't build up the photons over a 5-minute period before processing what we saw, and they're not sensitive enough to detect the colors from galaxies and nebulae like this. So there we go. There's the picture after the dark frame subtraction. Still really bright. Again, there was some haze, some cloudiness passing through the area. I'm looking again now, and there's a clear patch near the area, but there's also a cloudy patch near the area, and I'm not sure if the galaxy's in the cloudy part of it or the clear part of it at the moment, but it's kind of coming and going. The moon is looking better, less hazy around the moon right now from my view, but that's not where the galaxy is. It's high in the north, so we just have to see what happens. But at least I know for sure it's focused, so that's good. Yeah, I made this joke earlier that not on the stream, but I was making this joke earlier in the day that this actually happened a long time ago in a galaxy far, far away. About 21-ish million light years. Yeah, according to Sky Safari, M101 is 23 million light years, but your mileage may vary depending on source. It won't really be us one day. Our sun is not big enough to go supernova like this. But this is what we're expecting to see, a star-like object brighter than the core of the galaxy itself in one of the arms of the galaxy. You bet there's a KFC there now. Well, I don't know about that. Probably a lot of debris and a nebula. A supernova remnant. Heck, after 21 million years, I don't even know how much of the remnant would be visible. Probably not much. Yeah, the haze is real bad right now. I'm just looking at that first image that came in compared to images earlier in the stream. Yeah, it was not good. It all went to pot about 15 minutes ago, just from haze. If we can get that haze and cloudiness out of here, we'd be good to go. Alright, 23 seconds. Let's hope it improves. I do notice the guide star lost about 100 values of brightness since I first started imaging the galaxy. That indicates the camera's basically working harder looking through some crud. And it's not great. Let's see what we get here. Yeah, more of the same. If anything, brighter. Just background light level brighter, I mean. Yeesh. It's a soup. It's an absolute soup. Yeah. At this point, I don't even know if I'll include the last 15 minutes of images in the stack, because it'd probably make the quality worse, just from the amount of background light level. I mean, the good news is, at least for the stream, we can still see the supernova easily. And you can see the general spiralish arms of the galaxy. It's just not as clear as it was before from the clouds and the haze. But I'll be back in a few minutes, and maybe things will start to improve. Okay, I'm back, and it does look like maybe the quality has improved a little bit in the last couple exposures. Looking at the sky, it is more clear around the Big Dipper. Around the Big Dipper, where the galaxy is. But there's still some cloudiness lower in the north. So it might come back, I'm not sure. But what I will do is stack the latest pictures. Gotta see if some of these need to be omitted from the stack just for being so cloud-filled. Oh yeah, the last two are way better than the others that have been going on for the last bit. I'd say the last 45 minutes has been kind of a wash. These last 40-ish minutes has been kind of a wash. Just from the amount of haze and stuff. So I'm gonna omit those from the stack. That's let's see, that's 1, 2, 3, 4, 5. That's 25 minutes of light loss there. It's unfortunate, but so it goes. In fact, I'll wait one more minute for this last picture to come in. That'll give me a nice even 20 images, which will be, is that right? 100 minutes, just an hour and 40 minutes? Is that all they really gained from that? No, it's gotta be more than that. Hour 55. Oh, I'm looking at the flat frames, 19 flat frames, 23 light frames. Yeah, so that'll give me 2 hours of light. So I had an hour and a half before, this will be 2 hours of light. It's 2 hours there, so I'm going to go ahead and throw that one in the stack. Okay, now I'm going to process that in Pixen's site using the same method as before, so I've got an apples to apples comparison. Weird graphical glitching going on there. I was trying to... The image looked weird for a second, but it was just a graphical glitch. pretty darn good. Pretty darn good, I'd say. Okay, so I'll save this. Okay, so for reference, here was the first 90-minute stack. Oops. Now, the size of the new stack is going to be a little bit different because I did a intersection stack, so it only stacked and retained the parts of the images that overlap between the two positions of the galaxy. So when I went off and refocused the telescope and then brought it back to the galaxy, that generated a new position of the telescope, which is similar to, but not exactly where it was before. And so that results in some seams if you stack them all together in terms of like the noise profile. You'll get noisy edges of the image where there aren't as many images in the new section as there were in the old section. So instead, you just stack the parts that overlap that are common to all images. And it results in a slightly smaller picture, depending on how accurate you were in trying to get the galaxy back exactly where it was before. But other than that, it's the same. So here we go. There's the 2-hour stack. And the supernova is right here. So again, first hour and a half, and then 2 hours. 1.5 hours, 2 hours. Other than the change in the size, because again, I was doing an intersection stack, if you look closely, I don't know how well it comes through after streaming compression, but on my end, I can definitely tell the graininess of the image is reduced by stacking another 30 minutes of light. The definition in the galaxy is a little bit better. I reused the same histogram adjustments as before. It's just that there's a better noise profile now in the image from having additional pictures in the stack. So that's 1.5 hours, and that's now 2 hours. Like that. I like that a lot. Alright, let me turn around behind me and see what the clouds are doing. Okay, I think the cloud situation's okay for now. Okay, so you can see the additional graininess there from the 1.5 hour stack. That's good. I'm glad you could at least see that. So we are improving things by continuing to stack light. I'm going to try to shrink this down and put it somewhere. Tell you what, I got an idea. I've got an idea. I'm going to move this. Over here somewhere. Okay, and move this over here like that. There. That's better. Best of all worlds, or something. Hey, Leaf. So yeah, this is live images from my telescope. I'm an amateur astronomer here in Florida. So I've got an 8-inch Schmidt-Cassegrain telescope, an LX200 Classic, with an astronomical CCD camera, which is called an SBIG ST2000 XCM. It's basically a deep space camera, and I've got it on my telescope here. It's polar aligned, tracking the motion of the stars, and it's also got an adaptive optics unit that is actually taking pictures of a particular star that's just out of the frame once every 0.6 seconds, and issuing corrections to make sure that the drive system is working perfectly, to make sure that it's compensating for any errors in the drive system, as well as, to some extent, the atmosphere. And that's allowing me to take these individual pictures in the live images you're seeing on the right. Those are then stacked, which means they're averaged together, averaging all the pixels across hours of time to produce a higher quality, less grainy picture that you see there on the left. They're all from tonight, from this live stream. But by taking each exposure, which each exposure in this case is 5 minutes long, so it's taking a 5-minute long picture with the main imaging camera while the auto-guiding camera is running through the adaptive optics. So it's a 5-minute exposure, but then you're stacking dozens of those pictures over hours of time to get the high-quality picture you see there on the left. And that averages out the noise, the graininess of the image in the live image. You see all those grainy bits of color there. That's just random noise, and by averaging that out over time, over hours of time, we end up with a higher quality picture. The things that change between the pictures get eliminated through that averaging process, so the random noise, because it's random, gets averaged out. the stars and the galaxy itself and the supernova stays the same from image to image. It doesn't change in any perceptible way over even a few hours. So that stays through the entire stack and ends up in the final picture. Yes, we're seeing something that happened, he asked, the supernova happened light years away, right? So we are seeing something that happened years ago. Is that not right? It is right. This happened millions of years ago. So this galaxy is somewhere in the ballpark of 21, 23 million light years away. So we are looking at something that happened about 21 to 23-ish million years ago. And the light from that event is just now reaching us. So, from our perspective, it's just now happening, because this is the information reaching us now for the first time, millions and millions of years later. But if you could go there in an instant and see it now, the supernova's already long gone, and the supernova remnant has already spread out and contributed material to new stars. So when a supernova explodes like this, it throws off elements into the galaxy and into the surrounding interstellar material that will contribute to future star systems forming. In fact, because of the way it works in chemistry and physics, anything on Earth in the periodic table heavier than iron was made in a supernova that occurred before our solar system came to be. When you have a star fusing material, like our sun, fusing hydrogen into helium and so forth, that lets off energy. That fusion process produces energy, excess energy. But when you hit iron, and you start trying to fuse iron, you don't get any energy out of it. When you get to heavier elements, if you try to fuse them at high, very, very high temperatures and pressures, you're not going to get energy out of it. It's actually a net loss. So stars cannot benefit by fusing those heavier elements. In fact, they die before that point. So the only way to get those heavier elements naturally is with a highly energetic event that basically doesn't care that it's energy stealing or a net loss, because the energy is there whether you like it or not. And that's definitely the case here with the supernova, this massive explosion of this star whose core boy, get my tongue tied. This star whose core has collapsed. And that process is so energetic that it produces very heavy elements well past iron, and that contributes to the interstellar material and allows for heavier elements to be present in planets that formed after that supernova. So it is contributing to the formation of future star systems that have probably already started forming by this point. What causes random noise exactly like the other things in space moving around it? It's random noise in the camera, and it's not necessarily anything in space, though you do get cosmic ray strikes, which are more noticeable than the random fine graininess. Let me take a look here at the picture and see if we can find any hints of cosmic ray strikes on this frame. I don't see a great example on this particular frame, but sometimes you will see random bits of noise that are brighter than the rest, that only last for one frame and sometimes take up multiple pixels, but those are from cosmic rays, radiation from space actually hitting the sensor and lighting up a pixel for just a single frame. But that is much more noticeable than the random noise I'm talking about, the grain of the image, which generally is contributing from, a lot of it's from thermal noise, especially tonight. I'm having to run the camera warmer than normal. This camera is designed to chill the CCD to very cold temperatures below freezing, but I can't get it below freezing tonight because there's humidity in the chamber. There's a desiccant, silica desiccant, just like you would find in a bottle of pills, present in the camera to try to suck the humidity out, but it's saturated right now, so as a result I can't chill it below freezing or ice will start forming on the CCD. So normally I run it at even colder temperatures. Right now it's operating at 2 degrees Celsius. You can see the temperature reading there. So the cooler is only running at 40% power. I can normally crank that up and get it to sub-zero temperatures, and that reduces the amount of noise in the image, but it's still not going to completely wipe that out. Even at sub-zero temperatures, there will still be some thermal noise there. There's also readout noise, so as the electrons get transferred off the CCD, basically what's happening here is photons of light coming from this galaxy, coming from these stars, coming from that supernova, are hitting the detector. They're being converted into electrons that are stored in each pixel well. Those pixels have to be read off, and so the electrons are transferred to a readout mechanism that is reading the charge of each pixel. That process is not perfect, and as a result there's noise introduced in the read of the charge, and so the read noise is often a significant factor. And when you start to chill the CCD to reduce the thermal noise, the read noise can become the limiting factor, that no matter how cool you make it, the readout is still going to introduce noise to the process. So there's various contributing factors to noise, but none of them necessarily having to do with space, with the notable exception of cosmic ray strikes, which, as I said, are random one-frame events. So you can see there, when the frame changes on live, the noise pattern changes, but the galaxies and the stars stay the same. And each image is 5 minutes, so it takes 5 minutes to collect that much light and then read it out. But if you watch when it hits zero, when the timer's at 280 now, when that hits zero and it downloads the image, it'll update the live image, and you'll see the noise pattern changes. And so that's how we can beat that, by averaging those pixels over the course of many pictures, because those pixels change, they average out, and the light of the galaxy and the surrounding stars stays the same. Well, bad news, gang. Clouds have moved back into the image, as you can tell from the degraded quality and the brighter yellow light of light pollution and moonlight reflecting off the clouds. It's much more extensive, and we actually lost the guide star completely, so the telescope was starting to chase its own tail, hunting for the guide star, ruining the picture that was being taken. I didn't even bother downloading that picture. It was just ruined by that. And it's much more extensive throughout the whole sky now, so that's gonna pretty much do it for my ability to take pictures of the supernova tonight. But I will process the picture data that we have collected so far that's good, and we'll see what we get for a final stack here, so give me just a few minutes. Just a minor little correction there, Kitsune. The guide camera sits outside the main field of view, but it's actually inside the main scope. It's just slightly outside the main imaging chip, and so it uses a little miniature periscope to pick off a piece of light from the main telescope. A lot of people use guide cameras that actually do sit outside the main scope, but this one actually is inside the main scope, which has certain advantages because it doesn't suffer from flexure, which is where your guide scope is moving slightly differently from the main telescope just due to physical forces distorting the shape of the telescope as it rotates under the force of gravity. Gravity actually can torque the guide scope to sit a little bit differently over the course of the night, and then leads to trailing of the main camera. Anyway, I'm getting down in the weeds with all this, but anyway, sorry, just a little minor correction there. It is in the main telescope, it's just not in the main field of view. Alright, so this is 3 hours of light. Now, or, no, sorry, 3 hours. 2.5 hours of light. So, before we had 2 hours. And now we have 2.5 hours. So I'm going to size that as close as I can to the other one. Okay. So that's not 2 hours. This is, okay, so this is 2.5 hours. And actually, let me blow this up. To take up way more of the screen, so you can see it better. Okay, so this is the 2.5 hour image. Let me turn that guy off there, that guy off there. Okay, 2.5 hours versus 2 hours. Law of diminishing returns, it's a very minuscule difference at this point. This is 2 hours, this is 2.5 hours. Minuscule difference, but it is a difference. A little bit less noisy there. So, I will go through and do a final process later, probably tomorrow, actually today now. We're now in the early AM, aren't we? But after I get some sleep, I will do a more thorough processing of these images to do some proper tone mapping on it, and that'll bring out the color better, I think. But yeah, I'm pretty happy with that. I'm pretty happy with that image of M101. I think this is actually the first time I've made a serious attempt at photographing M101, as a matter of fact, especially with the adaptive optics system. So I'm pretty happy with this this result here, and got a good look at the supernova tonight. So very happy with this result. Let me see here. I do want to do one more little blink comparison, because the 2 hour to 2.5 hour mark doesn't result in a huge difference, of course, but let's take a look at where we came from with the 90-minute image. So this was the first hour and a half of light. And let's see. Okay, so this was 90 minutes. This was 2 hours. This is 2.5 hours. And so let's just blink between 2.5 hours and 90 minutes. So you can see how it's a little bit grainier there at 90 minutes, and then we clean that up by just taking more pictures and going for 2.5 hours instead. "90 minutes, 2.5 hours. Alright. I'm pretty happy with that. So, I'm going to start getting ready to tear down here, and want to thank you all for coming and taking a live look at the supernova tonight. Leaf asked a question here. He's been asking great questions tonight. So the guide star is a smaller camera within the telescope and isn't affected by torque and other gravity forces acting as the main telescope. Is that right? So, yeah, the guide star is captured by the guide star camera, the guide camera, and that is also in the telescope. It's in the same camera. It's the camera that I have basically has two sensors in it. One main imaging camera and one tiny small camera that is positioned above the main imaging camera. So it's able to take two pictures at once. And it basically picks off a little piece of light that isn't being used by the main camera and uses that at a higher frame rate, a much higher frame rate, to guide the telescope while it's taking the main picture. And because it's pulled from the same telescope, you don't have issues with trying to guide using a second telescope that's bolted to the main telescope, because if those bolts are not perfectly rigid, and they're not going to be, even a slight deviation, even a thousandth of a degree, is going to result in a bit of smearing. So you want the same light that the main imaging chip is gathering to serve as the source of guiding the camera, guiding the telescope. At least for my setup, that's definitely a benefit. How does it guide exactly? It looks at the center of the star. It calculates what the coordinates of the center of the star are in the image, and if it sees it deviate even a little bit, even a fraction of a pixel, it will issue a guiding correction to tilt and tip a mirror that is in the adaptive optics system to keep that star perfectly centered. Thanks, Toast. Appreciate your subscription. So yeah, if you guys enjoyed this, please like and subscribe. I'll be doing more streams, as always, in the future, and I'll post the stacked image to the community tab as well as Twitter. What is this guide star, then? It's not the supernova star. It's a star that's not even in this picture. It's just above and outside of the picture. It has to be... It has to be outside the picture, because it's got to be a piece of light that the main imaging chip is not using. It's just a random star. It could be any star. But for the purposes of guiding, you want it to be a star that's sufficiently bright that you can pick it up in even less than a second exposure. So, it's just any random bright enough star. So, alright, thanks everyone for watching, and hope you enjoyed it. Happy Memorial Day. Thank you to all of our troops who've laid down their lives in the service of our country and the protection of us. So thank you all. And until next time, clear skies.